Here's a quick walkthrough of the problem number 12 on the homework on chi-square testing. And this is similar to the one we did in class number 11, but this one has more categories, so there seems like there's more choices to be made. We're testing whether the probabilities of, I'm reading the problem here, probabilities of having a birthday in a given quarter are not equal. So in other words, are people's birthdays evenly spread out throughout the year? And they're looking at the first, second, third, and fourth quarter of the year. So our null hypothesis is always the hypothesis of no effect. So that's what this would mean, that there's nothing special about one quarter of the year versus another in terms of, get rid of that, in terms of when people have birthdays. So H0 is, we can think of it as no effect of whatever we're talking about. You could think of it as the quarter of the year you were born is equally likely, which year you were born is equally likely. So, but if there is nothing going on with our population in terms of their birthdays being biased towards one quarter or the other, then we would expect that each of the quarters of the year, roughly a quarter of the people were born. HA is always just the opposite of that. So the opposite of all of the quarters being equally likely is that at least one of them is different from some other one. So in other words, they're not all equal. That's what HA is saying. Though I didn't write those statements, I just picked them off the list. So the wording might be different than what you would write if you were setting it up yourself, and that's fine. But that would be these would be the right things. In this problem, the data is stuck inside of the little cell here. So if we pop that open, this is what that looks like. I just screenshot it and stuck it on here for you, but that's what you see when you click that icon. And in this case, after we've set up the hypotheses, they actually repeat that information. They put the observed counts in here. So notice these are the same things that came from the table. And they do tell us that adds up to 88, which is nice, so we don't have to do any arithmetic. But the expected counts, and remember expected here means expected assuming the null hypothesis is true. So the null hypothesis says your birthdays are equally spread out throughout the year. And so if that's true, then our 88 birthdays would have to have a quarter of them, 1/4 of them in each of the quarters of the year. So if we do 1/4 of 88, that'll give me 22. So if there really is no bias towards any particular time of year to have a birthday, whoops, where did I get 26? Oh, Lord. If there's no bias towards any particular time of the year to have a birthday, then you would expect that I'll just write over here, that the 88 people, that given 88 people, 22 would be born January, February, March, 22 would be born April, May, June, 22 would be born July, August, September, and 22 would be born October, November, December. So they should be evenly spread out. So our chi-square test, remember, is just going to be the measurement of how far apart the observed value is from the expected value in each case. Like here you can see they're exactly the same, here they're pretty different, here they're pretty different. So the question is, are they different enough for us to believe that the birthdays really are not distributed throughout the year evenly? Okay, so if it's me, I'm going to open up that applet that I showed you in class. You have a link to it on both of the handouts that I gave you, and those handouts are posted. So if you don't have the handout and don't know where they're posted, you can send me an email and I'll email it to you. But the handout is the only place where you'll find that URL for the. It looks like this. And as we said in problem number 11, just for number 11 and 12 are the only two that do this, but they use this tab, the one that says goodness of fit. The other one over here was the other thing that we were doing earlier, but this thing called goodness of fit is what we're using for problems 11 and 12. So we have 4 categories, specifically there should be counts for the 4 quarters of the year for birthdays, so that's what's going to go in these boxes, are those numbers from my problem. This applet allows me to actually label these, which is nice, so I can keep everything straight. So I can put here January through March, April through June, so I can actually write the words in there for what each one means, where I could say quarter 1, quarter 2, quarter 3, quarter 4, however you want to do it, but it gives you the opportunity to label them. So here we would label quarters of the year. We would put the counts in from the problem, the observed counts. Then down here, the null hypothesis asks what proportion do we think should happen if the null hypothesis is true. And the null hypothesis is that you should have 25% of the birthdays in each 25% of the year if there's nothing going on here. So this one, this default that is 25% in each category is fine. This one I have to actually enter. Notice that the number of categories is settable. I believe the default is 4 when it first comes up, which works out well for this problem, but on other problems you will change that to whatever number of categories you have. So once you fill it in, it'll look like this. Here are my counts. You can see that I went ahead and labeled my categories. I just typed that in so that each one referred to something. So now that looks exactly like the table that I was looking at a second ago. And my null hypothesis is that everybody is even. Now, as you enter those things, the applet is actually updating stuff. So I hit it here so that it wouldn't distract us. But once you have that stuff in there, it will, oops, get rid of that. This is what it says. So here we have the observed counts. Notice it copied my little categories over, so that's nice. So I can see that it really does match my problem setup. The number down here tells me what I would expect the counts to be if the null hypothesis were true. That matches what I typed into the applet. And then the most important thing is that it tells me the chi-square test statistic, it tells me the degrees of freedom, and it tells me the p-value. And so in the homework problem, it's going to ask you to fill in those 3 things as your measurement of the evidence compared to the null hypothesis. So when you enter those, it'll tell you how fantastic you are, and then you'll get to the end. So I just scroll down to the end. You can't see my chi-squared on here, but I did enter that. I entered the degrees of freedom from the applet, and I entered the p-value from the applet, and all you got to do is pay attention to how many decimal places it wants each of these things to be. And then stating the conclusion, they're telling me I want to use the significance level of 0.05. So 0.05 is what I would mean by small for this hypothesis test. So my p-value here, it would not be considered small by that criteria. So if I had to add a sentence to what they wrote, I would say the p-value, my p-value, that's that number, is not small. And again, small means this. So my p-value is 0.066. Small means 0.05. And because the p-value is not small, so, and then we start the rest of this. So if the p-value is not small, then we do not reject H0, which means there is not evidence to conclude. And again, like I keep saying, this is just, what's in the box here is just HA. And that is not right. What's in the box here is just HA. And in this case, it's literally HA. If you go back, because it was multiple choice, so it was really what the HA said at the top of the problem. So once again, if we decided that our p-value was small, then the only thing that changes in our conclusion is this word, and this word would be erased. So the words in red are either all 3 there or all 3 gone, erased. Those are the only 2 ways that this ends.